Today on the Perception and Action podcast, are there any human factors issues left to consider when we've completely taken the pilot out of the plane? Don't be silly, of course there are. On the sports side of things, why knowing when not to do something on the field can be critical to success. So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception and Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. In today's episode, I want to look at human factors issues related to flying uninhabited air vehicles, commonly called UAVs or drones. UAVs are aircraft that are controlled remotely by one or more human operators, or flown via automation. Although UAVs have received a lot of press in recent years for their use in the military and by companies like Amazon, the concept has actually been around for a very long time. The Kettering bug, developed in 1917, could actually fly on its own and was guided by a small onboard gyroscope. One major difference between modern UAVs and these early ones, however, was that the aircraft like the bug were actually more like cruise missiles, as they're designed to carry explosives to a target and not be recovered. These initial attempts were often seen as expensive and unreliable toys. For example, the Kettering bug was actually never deployed in combat because military leaders feared it might accidentally crash into Allied troops. It was not really until the 1980s that the attitude towards UAVs changed and that they were taken more seriously. In particular, their potential for doing photo reconnaissance was recognized early on. The Predator UAV was the first deployed aircraft of this type by the United States in 1995. Of course, since then, UAVs have been popular for many other purposes, including border patrol, search and rescue, cargo delivery, disaster monitoring, agriculture, and within the last couple of years, recreational use. There are obviously numerous important issues to solve related to UAVs, from privacy to regulation of airspace, but today I want to focus on the issue of flying a UAV. What perceptual and cognitive issues do UAV operators face, and what are we going to do to train and improve these skills?
Oh, one of these days I'm just gonna help and lead you with my big J-O-E.
Evidence has shown that flying a UAV is not easy. In some analyses by the U.S. Department of Defense, it has been found that UAV mishap rates are 30 times higher than for inhabited planes. What are the unique challenges for a UAV pilot? The separation between an operator and the vehicle creates some problems for human performance that must be overcome, including a restriction in the sensory cues for flight control and communication delays, and an impaired ability to scan the environment around the aircraft. To explore how these issues might affect pilot performance, I want to touch on 5 key issues. The first is one we talked about last time: automation. UAVs vary dramatically in the extent to which the flight control is automated. At one extreme, you essentially just have a camera feeding back a video to a pilot who is controlling the aircraft manually using a stick and rudder control as if he or she were in the actual plane. At the other end of the spectrum, there are completely automated UAVs that use pre-programmed coordinates to fly, like the ones Amazon is proposing for their Prime Air program. In between, however, there are several different types of partial automation. For example, there are some in which the remote operator still has to input control, but is done by buttons and menus on a computer display rather than a control stick. Complete manual control of a UAV can be extremely challenging due to transmission delays. For long-distance flights, there can be a significant time between when an image is sent from the aircraft and when it gets back to the remote pilot, of up to 1 or 2 seconds. This can lead to the pilot making a control input that was appropriate a few moments ago, but may not be appropriate now. Think of playing a video game with a major lag. And of course, as we saw in the last episode, full automation comes with drawbacks too. In particular, potential loss of situational awareness and vigilance in the pilot. And there are certain functions, For example, interpretation of video imagery, which are unlikely to be completely automated in the near future. For these reasons, many have recommended that hybrid manual automated flight should be the accepted standard for UAVs. This issue of automation may come more to a head as UAVs begin to become more prevalent in our airspace. Will automated see and avoid procedures be effective, or will it be up to the pilot to watch for other aircraft on a small 2D screen? The second issue I want to look at is the human-machine interface. Assuming that we want a pilot to be involved, how should they control a UAV? What we're talking about here is really a change in the nature of what it means to be a pilot. Do we want them to control a UAV using the traditional stick and rudder, or do we want to hand pilots an Xbox controller? There is also a related issue of what the remote pilot's viewpoint should be. There are basically two possibilities: internal and external systems. The pilot could be given the view from a camera mounted in the cockpit, so first-person point of view, or if they're relatively close to the UAV, they could be given a third-person view, either from their own eyes or via a camera. For external third-person systems, the flight controls are often similar to that used for radio-controlled hobby aircraft. With such systems, there can be an interesting human factors issue, in that the mapping between the controls and the inputs can change. Imagine you're standing in a field holding a remote control for a drone that is flying directly away from you. If you push the control stick to the right, it will turn to the right. But now imagine the drone is traveling at an angle. What will happen when you push the stick to the right? What about when it's heading straight back towards you? Pushing right would make it go left. The problem here is, of course, that the pilot's external viewpoint is not egocentric. That is, it is not changing with the motion of the plane. This creates a massive stimulus-response compatibility problem. Or, referring back to my episode on ecological psychology in 20C, we've broken the natural perception-action coupling that occurs as we move through the world. Another interface issue that arises with UAVs is the display given to the remote operator. Even though cameras and displays are rapidly improving, there are still trade-offs between resolution or detail, update rate, and field of view. That is how much of the scene you're going to show to the operator. As we've already discussed, low update rates can impair motion perception and lead to poor control. Low spatial resolution can make it difficult to detect critical objects in the environment. And as I've discussed throughout these episodes on driving and aviation, optic flow in our peripheral vision is critical for control of heading and speed, so a display with a small field of view will make it difficult to control the aircraft and require a lot of scanning behavior. So in a nutshell, it's critical that designers find a good balance between these different UAV display parameters. One way in which designers have looked to address some of these interface issues is to use the same approach I talked about in the episode on driver warnings, looking towards multisensory, auditory, and tactile displays. For example, in 1999, Sklar and Sartor developed a tactile display which delivered vibrations to the inner or outer wrist of the pilot to signal a change in automation status. These tactile displays resulted in more accurate and faster detection of automation mode transitions. More recently, Gunn and colleagues used force feedback pulses through the control stick and brief bursts of sound to aid target acquisition performance in UAV operation.
Creatures on the wing are we, taking flight across the sea, but you'll never find a right way of leaving me.
Another interesting psychological issue introduced by UAVs concerns risk-taking behavior. As I talked about in the context of driving back in episode 29, human operators are often willing to accept some level of risk. Will this increase because the pilot and the UAV no longer share the same fate? For example, this could change a pilot's decision about whether or not to proceed in bad weather. There is also, of course, the related issue of conducting military missions in which one is executing a strike on a target while completely removed from the combat situation. A fourth issue is crew and traffic management. One of the obvious advantages of using UAVs is that they can make longer distance and longer duration flights as compared to a manned crew aircraft where issues of fatigue need to be considered. But in order to achieve this, there will need to be some handover of control, in flight, between remote human operators. As I've discussed a few times now in the podcast, these points of handoff between operators, whether it's between an automated system and a human operator or between two human UAV pilots, are difficult and critical points because it will take some time for the new operator to get up to speed on the situation. The final human factors issue I want to mention that relates to UAVs is that of crew composition and skill. As I discussed back in my interview with Nancy Cook in episode 22A, UAV operations often involve a multi-person crew in which each person is assigned a particular function. For example, one person might be responsible for control of the flight of the aircraft, while another is responsible for taking photos. As we discussed, this requires effective coordination and communication between team members to ensure success. One interesting approach Nancy has been taking to solve this issue is the use of an automated or synthetic teammate that can help with communication flow. A related question is, how should UAV operators be trained? Do they need to go through traditional flight training? Research regarding transfer from manned to unmanned piloting has had somewhat mixed results. In 2002, Schreiber and colleagues found that flight experience in a traditional aircraft reduced the number of training trials required for operators to reach a criterion level of performance on a basic set of maneuvers and landing tasks in a Predator UAV. However, other studies have found that flight skills gained in traditional flight training are not necessary for being an effective UAV pilot.
Oh, you're a sheep in wolf's clothing, hard set on hiding. Our bodies are knitted, our minds are colliding. You wind up my eyes like birds in a wire, drawn out my breath like moss to a fire.
Before I finish the aviation portion of today's episode, I want to talk about another type of alternative flight. Helicopters. The human factors with helicopters can be quite different from regular fixed-wing aircraft. Helicopters can perform a wider range of maneuvers, including remaining completely stationary in the air. They often operate in much more difficult environments, including very poor weather, low-level flight, and search and rescue, and they're inherently more unstable in the air. It has been estimated that over 70% of helicopter accidents are due to human error. So let's look at some of the issues involved. A first issue is the types of flight helicopter pilots can be asked to perform. Under the general class of terrain flight, there are 3 different subtypes. In low-level flight, the pilot is required to maintain a fixed altitude, for example 200 feet, and fly at a fixed airspeed. The next type is called contour flight. This involves following the contour of the ground, so going down into valleys then back up when there's a hill. The final and most difficult type of helicopter flight is called nap of the earth. This involves flying as close as possible to the ground so that one is concealed by objects like buildings and trees. In some cases, this can involve flying at an altitude of only 20 feet. Obviously, this task involves incredibly high workload and places high perceptual and motor demands on the pilots. In general, helicopter pilots rely much more on what are called out-of-cockpit cues. For example, when performing nap of the earth flight, pilots seem to rely on 2 particular sources of visual information. The first is called motion parallax. Next time you are a passenger in a car or riding on a train, have a look out the window and fixate some distant object like a tree. Now pay attention to how things are moving. What you should notice is there's a nice lawful relationship between the motion and the depth of objects. All objects that are closer to you than the object you're fixating will move in the opposite direction to the direction you are traveling, with objects closer to you moving faster than ones that are closer to the fixation point. For all objects that are further away from your fixation point, the motion direction will be the same as your direction of travel. And again, objects further from your fixation point will be moving faster. So this pattern of moving objects across our eye provides a strong cue to relative depth the pilot could use. The second cue is the one that I discussed back in episode 31 when considering visual cues to altitude. Texture gradient. When a helicopter pilot looks out their window, texture elements, for example trees in a forest, will become more tightly packed the further they get from their eye. It is also the case that the rate at which the texture density changes, what we call the gradient, is directly related to the slope or steepness of surfaces in the environment. So you can see these cues provide direct information to aid in control, without the need for explicit estimates of absolute distance, which, referring back to my episodes on driving, we are very bad at. Despite these effective information sources, visual perception in helicopter flight can be extremely demanding due to the poor viewing conditions and the size of objects. During Nap of the Earth flight, a helicopter pilot must be aware of objects like wires and cables, which project a very small size on the retina. In the Vietnam War, it was reported that one particular set of power lines was responsible for 55 helicopter fatalities. Flying a helicopter at night also makes it difficult to use the out-of-cockpit visual cues. It can also be the case that shifting one's gaze from a cockpit with bright instruments to a dark out-of-cockpit scene can cause problems. Because our eyes must adapt to the lightness change without any assistance, it can take up to 3/4 of a second before vision becomes clear again. During this time, the helicopter would have likely traveled 50 meters. It is for these reasons that helicopter flight has been one of the main driving forces behind the development of night vision goggles. NVGs have improved a lot over the years, but they were initially fraught with problems of their own, including whiteouts when a really bright object was present, distortions of depth perception, and small fields of view. Once infrared sensors were used to recreate the visual scene, NVGs became much more effective.
Still the tears come burning my heart, and I can't help them, so I wait for the night.
Before finishing this section, I want to mention one more particular piece of technology that was specifically developed for helicopters. Another maneuver that is of course unique to a helicopter is the ability to hover. Without flight stabilization, this can be a very difficult task, as it requires the pilot to make small corrections based primarily on the use of visual cues, for example the motion parallax we talked about earlier. This can be difficult when they're hovering in an open area with few visual features, and/or are asked to perform some other visual tasks like reading a navigation display. To combat the high visual workload, Angus Rupert developed the Tactile Situational Awareness System, or TSAS. The TSAS is comprised of a vest or belt that a pilot would wear under their flight suit. It is equipped with several devices called tactors. In one version I was lucky enough to try out, these were actually pneumatic, so they would blow small puffs of air on you. The idea was that the TSAS would give the pilot tactile cues they could use for hovering. So when the helicopter started to drift too far to the left, the pilot would get a tactile signal on their side. This device is shown to allow pilots to hover more accurately and maintain a smaller range to targets. The pneumatic device also had the added bonus that the air was cooled, so it helped keep pilots cool under their flight suit. A final set of challenges associated with helicopters are the extreme physical demands they can place on pilots in terms of vibration, noise, and temperature. As one pilot colorfully put it, a helicopter can be thought of 1,000 parts vibrating in formation. Prolonged exposure to high levels of vibration can have numerous acute and chronic effects on a human operator. In the short term, it results in fatigue and even reduces our visual acuity. In the longer term, it has been linked to back pain and degenerative diseases. Turning to auditory effects, inside a helicopter, the sound level can reach 120 decibels, which is getting close to the level of a jet takeoff. This is obviously why helicopter pilots wear headphones and hearing protection, but this in turn can create issues with communication. Okay, time to land this chopper and talk about knowing when not to do things in sports.
Everybody's always trying to slow me down, I just give them hell. Everybody's always asking what is wrong with me, it's just as well. Don't stop, don't stop, ladies, you gotta leave. Don't stop, don't stop.
One of the aspects of sports performance I've been really interested in over the years is action inhibition. How does a rugby player know not to move when their opponent fakes to the left? How does a quarterback know not to throw the ball and look somewhere else? And, in the specific case I've studied, how does a baseball batter know when not to swing at a pitch? As I discussed back in episode 4, I actually developed a full model of this behavior that is based on both the batter's expectations about the upcoming pitch and the visual information early in the ball's flight. Well, there's an interesting recent study that has further examined this behavior, which I want to look at today. This paper by Murskin and colleagues, published in the journal Neuroimage, compared EEG recordings for 9 college baseball players and a group of 10 non-players. The stimuli were pitches, solid green circles on a gray background, presented on a computer monitor. 3 pitch types were simulated: a fastball, curveball, and slider. Each of these had different simulated trajectories. The experimental procedure was as follows. Before each simulated pitch, participants were presented with a letter F, C, or S, corresponding to the 3 pitch types, which told them what pitch type they should be looking for. They then performed a go, no-go task, in which they were required to press a button if the pitch matched the cued type and do nothing, or inhibit a response, if it did not. Conceptually, this matches the act of sitting on a pitch in baseball, where a batter is locked in on one particular pitch type. What was found? In terms of the actual go, no-go task, experts were significantly faster, by about 40 milliseconds, and significantly more accurate, by about 15%, as compared to novices. For the EEG recordings, there were several interesting expertise differences. In particular, they found differences in the inhibitory processes on the no-go trials, in which no response was required. For this, experts showed greater activity in a brain area called the supplementary motor area. There were also significant expertise differences in an EEG component called the contingent negative variation, or CNV. The CNV occurs before the stimulus appears on the screen, and is thought to represent a preparation process. Based on these findings, the authors have developed a product for assessing decision processes in athletes called DeServo, which I'll be talking more about in the podcast in another episode.
You're holding tight to what you know. You never find it if you never go. Never hold hands with the one that's letting go.
So, to sum up, in today's episode, I looked at 2 alternative forms of aviation, UAVs and helicopters, touching on some of the unique issues associated with each. I hope you see the overall message I've been trying to get across in talking about all of these things. As long as a human being is going to be somewhere in the loop, you are never going to get rid of human factors issues with new technologies. You're just going to change them. On my next full episode, I want to move away from flying an aircraft to look at the perceptual and cognitive challenges associated with being an air traffic controller. On the sports side of things, on today's episode we saw that the ability to inhibit actions may be one of the strongest markers of skill in sports like baseball. On my next episode, I want to look at the Great British Medalist Project. What can we learn from athletes that have reached the pinnacle of success in sports? Remember, you can head to perceptionaction.com to find out everything about this podcast, including the show notes, some info about me, different ways you can listen, what's coming in future episodes, and ways to contact me. This is Rob Gray from ASU. Cheers for now.